All right, let's dive into a really cool piece of tech. Imagine being able to see into the most impossible places using nothing more than a tiny little strand of glass and a pulse of light. Well, that's exactly what we're talking about today with fiber optic sensors. These things can measure our world with just breathtaking precision. But first, let's think about a problem. How do you measure something inside a running jet engine? I mean, it's insanely hot in there. Or what about monitoring the strain on a bridge while it's getting blasted by a hurricane? You know, these places are way too hot, too loud, or just full of electrical noise for your typical sensor. So yeah, how do you see what's going on in these, well, impossible places? Well, the answer is pretty amazing. You do it with light. A fiber optic sensor system at its heart has two main parts. First, you've got the fiber unit. That's basically just the cable that carries the light. And then there's the fiber amplifier unit, which is kind of like the brains of the operation. It's the control center. It's got the emitter, which makes the light, a receiver to catch it when it comes back, and the sensing circuit to figure out what it all means. Okay, so to really get how these sensors work, we've got to look at how light actually moves inside that tiny fiber. It all comes down to this really amazing principle of physics.
And that principle is called total internal reflection. Now, I know, it sounds super complicated, but the idea is actually pretty simple. All it means is that you can trap a beam of light inside something and make it just bounce off the walls over and over again without ever escaping. It's this little bit of magic that lets an optical fiber act like a perfect pipe for light, guiding it exactly where it needs to go, even over really long distances.
And this is exactly how it's done. The fiber is actually made of two layers. In the middle, you have the core, which is made of glass with a high refractive index, which really just means it's really good at bending light. And that core is wrapped in another layer called the cladding, which has a lower refractive index. That difference, that's the whole secret. When light traveling in the core hits the boundary with the cladding, it just can't get out. Instead, it reflects perfectly back inside and just keeps bouncing its way down the fiber. So after all that bouncing back and forth, you might think the light just shoots out in a perfectly straight line, right? Well, not exactly. It actually comes out of the fiber in a pretty wide cone, about 60 degrees. And this isn't an accident. It's totally intentional. This spread gives the sensor a much wider field of view, which makes it way more effective at spotting objects or picking up on changes in its path. So, okay, we know how the light travels down the pipe, but how does that light actually sense anything? Well, it turns out there are two main ways to do it, and the difference is all about where the sensing actually happens. First up, you've got what are called intrinsic sensors. With these, the fiber itself is the sensor. So some outside force, think heat or pressure, directly messes with the fiber, and that changes the light that's passing through it. Then, on the other hand, you have extrinsic sensors. Here, the fiber is really just a delivery system, like a light pike. It carries light to some external gadget, a transducer that does the actual sensing. Then, the fiber just carries the modified light signal back to the base. So to make that a bit clearer, think of it like this. An intrinsic sensor might measure temperature because the heat is literally stretching the glass of the fiber itself. Simple, right? But an extrinsic sensor, well, that might send light to a tiny little mirror at the end of the fiber. And if sound waves make that mirror vibrate, it changes how much light gets reflected back. And boom, you've just made a fiber optic microphone. Okay, so we know where the sensing can happen, either in the fiber or outside of it. But that brings up another really important question. What about the light are we actually measuring? And this leads us to two totally different methods. The first, and probably the most common way, is called intensity-based sensing. And the idea here is super simple. You just measure how bright the light is. If the light gets dimmer or brighter, that tells you something has changed. That's it. It's straightforward, it's reliable, and you can use it for all sorts of things. Here's how it works in practice. You have one fiber, the emitter, that shines light onto a surface. Right next to it, you've got another fiber, the receiver, just waiting to catch any light that bounces back. Now, if that surface moves or vibrates or even just gets less shiny, the amount of light, the intensity that the receiver picks up is going to change. And by measuring that change in brightness, you can figure out exactly what happened. But what if you need to measure something with just like insane precision? For that, we have to go to a much, much more sensitive technique, phase-based sensing. This method doesn't just look at brightness, it looks at the actual wave of the light itself. Now, this setup is absolutely ingenious. You take a beam of light and you split it in two. One half goes down a reference fiber that's kept perfectly stable. The other half goes down a sensing fiber that's out there in the environment. Now, any tiny little stretch or squeeze on that sensing fiber from vibration or strain changes the distance the light has to travel. This creates a tiny phase shift in its wave. When you bring those two light beams back together, they create an interference pattern. And by analyzing that pattern, you can detect movements that are, get this, smaller than the width of an atom. It is an unbelievably sensitive way to measure things. So, now that we've seen a bit of the how, let's circle back to the why. Why does any of this matter? Well, the advantages are exactly what make this technology such a game changer, especially for those impossible places we talked about at the beginning. I mean, the advantages are just huge. For one, because they use light instead of electricity, they're completely immune to any kind of electrical noise or interference. Plus, they're super compact and flexible, so you can sneak them into really tight spaces. And since there's no electricity at the actual sensor, they're perfectly safe to use in places where a spark could be, well, a really bad thing. And finally, light can travel for miles down a fiber with almost no signal loss, which makes them perfect for sensing things from really far away, measuring pretty much anything: temperature, pressure, vibration, you name it. You know, from checking up on the health of our bridges and buildings to creating new medical tools that can work inside the human body, these little sensors are giving us a whole new way to see and understand our world. And that just leaves us with one really fascinating question to think about. What new frontiers will these tiny, light-guided sensors help us explore next?